In this session, we are going to discuss the field of a polarized object, and hence we will derive the concept of bound charges. In the previous sessions, we have considered the effect of an external electric field on an individual atom or molecule, and also we have discussed what is a polarized object. We have already discussed what are nonpolar molecules and polar molecules. Now let us look their effect in the presence of external electric field. For a neutral atom or nonpolar molecules, as we know, the electric field will induce tiny dipole moment to each of them, pointing them in the same direction of the field. If the material is made up of polar molecule, each permanent dipole will experience a tiny torque, which makes them align in the same direction of the field. Notice that these two mechanisms produce the same basic result, and we will say the material is polarized. And we defined polarization as the dipole moment per unit volume. Now, in this session, let us consider we have a piece of polarized material as shown in the figure. My question is, what is the field produced by the object? Not the field that caused polarization. Let us sort it out. We know that the negative gradient of potential is the electric field and also the field due to an individual dipole. So let us divide the material into small infinitesimal dipoles. Since it is much easier to work with potential, let us calculate the potential at the point due to that single dipole. Let the point be at a distance r, and the expression for the potential to a dipole of dipole moment p is given as V of r is equal to 1 by 4 pi epsilon 0 p dot r cap by r square. This small letter p represents the dipole moment. Now consider an elementary volume d2 inside the polarized object. So the polarization p is given by p is equal to p d2. So the total potential can be calculated as V of r is equal to 1 by 4 pi epsilon 0 integral over the whole volume P of r dot r cap by r square d2, and that P of r we got it from the expression P is equal to P d2. Now let us look how to carry out this integration. As I told, V of r is equal to 1 by 4 pi epsilon 0 integral V P of r dot r cap by r square d2. Remember, these bolded letters are vectors and the unbolded letters are scalar. We can use the relation r cap by r square is equal to gradient of 1 by r. So substituting that r cap by r square as the gradient of 1 by r, the equation for V of r becomes V of r is equal to 1 by 4 pi epsilon 0 integral P of r dot del of 1 by r d2. Now there is an special technique to solve this integration. We have already learned this type of equations, or the functions which deal with this gradient have some general formula, and that general formula is del dot phi a is equal to phi of del dot a plus a dot del phi, where this phi is a scalar function, a is any vector. So this equation can be rewritten as taking the second term to the LHS and the first equation, the RHS to the LHS to the RHS, we will get a dot del phi is equal to divergence of phi a minus phi of divergence of a. So here instead of phi we have 1 by r, and for a, in the place of a we have the capital P polarization. Now you substitute that capital P in the just equation for the V of r, and the equation for V of r can be solved by integration in parts. Okay, you will get two parts, that is V of r is equal to 1 by 4 pi epsilon 0 closed integral 1 by r p dot dA minus integral 1 by r p dot p d2. So from where this closed integral came? This closed integral came from the divergence theorem, and we have obtained this final expression. So you carry out this mathematical steps and reach into this relation, that is V of r is equal to 1 by 4 pi epsilon 0 closed integral 1 by r p dot dA minus 1 by v 1 by r del dot p d2. Now this equation consists of two parts, and we will just look what are these two meaning of these two parts. The first term look like the potential due to a surface charge. So this can be written as sigma of B is equal to P dot n cap, and the second term look like the potential of a volume charge, that is rho B, which is equal to minus del dot P. And what is this sigma P? The sigma P is called the surface bound charge density, and rho B is called the volume charge density. So this means that potential of a polarized object is due to the sum of volume bound charge density and the surface charge density. So instead of doing the whole integration about the contribution of all infinitesimal dipole, we could find the value of bound charges and then find out the value of field produced. Now let us look into another situation, like what is the field produced by a polarized sphere of radius r. Whatever may be the problem, we have to first find the potential at that point, and we know that potential is the negative gradient of electric field is the negative gradient of potential. We can easily solve such problem. Okay, now we'll just consider a sphere of radius r which is polarized. So how will we polarize? We will keep this sphere in an external electric field. Now let us calculate the potential at a point outside the sphere which is at a distance r from the center of the sphere. As we know, the knowledge about the potential at the point will lead to us the information of the field at the point from the famous relation E is equal to the negative gradient of potential. So E at that point, that is outside the sphere, we can find out E out is equal to minus negative gradient of V out. V out can be calculated as our previous relation V of r comma theta, that is, I just noted this out because this V of r comma theta is the potential at the point outside the sphere, is equal to 1 by 4 pi epsilon 0 integral over the volume P of r dot r cap by r square d2. Since the sphere is uniformly polarized, we are dealing only with a uniformly polarized sphere. We don't want to write P of r because P is a constant there. So I rewrite this P of r which is equal to P. So the equation becomes V of r comma theta out is equal to P dot 1 by 4 pi epsilon 0 integral r cap by r square d2. But we are not going to rewrite this P of r cap by r square d2 in terms of this gradient of 1 by r. Instead, we are looking into another perspective. The electric field due to a uniformly charged sphere is given by the expression E is equal to 1 by 4 pi epsilon 0 integral over the volume rho of f r cap by r square d2. this expression for electric field we have done in our previous session, and so I can take this rho f is a constant, so I can take this rho f down, that is E by rho f is equal to 1 by 4 pi epsilon 0 integral r cap by r square d2. So for that term 1 by 4 pi epsilon 0 r cap by r square d2, replace that term with E by rho f. So what you will get? You will get V of r comma theta out is equal to P dot E by rho f. We know that E is equal to 1 by 4 pi epsilon 0 q r cap. And what is this q? This q is the total charge within that sphere, which is equal to 4 by 3 pi r cube rho f, and this capital R is the radius of the sphere. So substituting all this value, substitute this value of q into the E, and the pi and pi will go, the 4 and 4 will go, and all that you do that all rearrangements, and we will obtain that V of r comma theta out is equal to P dot r cap into r cube by 3 epsilon 0 r square. And since we know that P dot r cap, this r cap is a unit vector, P dot r cap is equal to P cos theta. So V of r comma theta out is equal to P cos theta into r cube by 3 epsilon 0 r square. Therefore, E out can be deduced from the relation minus gradient of V of r comma theta out. That is, you apply the gradient over the two LHS and RHS, which gives you P of r cube by 3 epsilon 0 r cube into 2 cos theta r cap plus sin theta theta cap. Remember, you should not apply del is equal to dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. Instead, you have to use the expression of gradient in the spherical polar coordinate system. Now let us check what is the nature of the field inside this sphere. We can arrive this in 1 minute, that the field inside is uniform, but here we have to calculate that. Since this is a uniformly polarized, we can say that field is uniform. Using the same method, E inside is equal to minus negative gradient of V of r comma theta inside. So what is V of r comma theta? Which is equal to 1 by 4 pi epsilon 0 integral P of r dot r cap by r square d tau, and d tau is that small elementary volume. And here this r is the distance within the sphere, but here E inside can be calculated as q dash r cap by 4 pi epsilon 0 r square, and that q dash is the space that encloses that radius, and here charge is not q. Remember, this charge is not q, so q dash is equal to 4 by 3 pi r cube rho f. Therefore, on substitution and for the proper values of E and q dash, we will get V of r comma theta inside is equal to r p cos theta by 3 epsilon 0. The steps are same as for the field outside. So, but we know that this r cos theta is equal to z, that is the z direction in the spherical polar coordinate system. So V of r comma theta becomes inside become P of z by 3 epsilon 0. Now how will you do this electric field inside the sphere? The electric field inside is equal to the negative gradient of V inside. You just take the gradient, and here we have written the expression in terms of z, so I can use the Cartesian coordinate Cartesian system for the del expansion of gradient. So E in is equal to minus P by 3 epsilon 0 k cap. Here P is a constant because it is a uniformly polarized sphere, epsilon 0 is a constant. So as I told, in the electric field inside the sphere is an constant, or uniform electric field is produced. So far we had discussed about the potential due to an polarized object in general, and after that we have calculated the field produced due to a uniformly polarized sphere. Now let us understand what really is this bound charges. In simple terms, bound charges are the charges accumulated due to polarization, and we now know how to calculate the bound charge densities. To understand the physical interpretation of bound charge, you consider a long strip of dipole, and after polarization the head of each dipole cancels inside and the only remaining is the end charges. So during uniform polarization we have only surface bound charges. To have an volume bound charge, the polarization must be non-uniform. Let us prove that for uniform polarization only surface bound charge exists. Assume that uniform polarization is along a cylinder of length L and area A. The bound charges that piles up at the end is Q is equal to PA. So the bound charge density sigma B is equal to Q by A. This is our famous relation charge per area. So sigma B can be written as P, and P is here this P is a scalar, so sigma B can be written as P dot n cap, that polarization along any unit vector. So if the polarization is non-uniform, we get accumulations of bound charges within the material as well as on the surface. At a glance, the divergence of P gives the information about the bound charges. So the net bound charges integral rho b d tau in a given volume is equal and opposite that pushed out through the surface. So we can write that in mathematical term as integral rho d tau is equal to minus closed integral P dot dA. So using the divergence theorem, integral del dot P d tau is equal to closed integral P dot dA. Therefore minus del dot P is equal to rho d. So these are the two proofs for the surface bound charge and the volume bound charge density. There are many other methods you can arrive in the same result, and for a sphere also you can use the same technique to find out the surface bound charge and the volume bound charge. Now just try this problem. A conducting sphere of radius r is placed in a uniform electric field E0 directed along the positive z axis. So you are keeping a sphere along the uniform electric field, and this uniform electric field is directed along the positive z axis. Just take a paper and draw the z axis from bottom to top. The electric potential for this sphere outside the point is given as V is equal to minus E0 of 1 minus R cube by R cube into R cos theta, and this capital R is the radius. You have to calculate the charge density on the surface of the sphere, not on the outside or not in the inside of the sphere. You have to just calculate the charge density on the surface of the sphere. Sorry, the charge density can't be at the out or inside. You have to calculate the surface charge density basically. So you have to calculate what is sigma B. That is the question. So it is the time to wind up. So in this session we have discussed potential due to a polarized object, and we have obtained the equation in terms of surface bound charge density and volume bound charge density. So remember, the surface bound charge density sigma B is equal to P dot n cap, and the volume bound charge density rho B is equal to minus del dot P, and this capital P is the polarization vector P. After that we have discussed the electric field at a point inside and outside of a uniformly polarized sphere, and we obtain inside the sphere this electric field is uniform and electric field produced is uniform. And remember, this is not the case if it is in a non-uniformly polarized sphere. You have to calculate or just try for a non-uniformly polarized sphere. After that we have just discussed the physical interpretation of surface and bound charges. So, for uniformly polarized object, you will get only the charges will be the surface bound charges, and for a non-uniformly polarized object there will be bound charges. And at last I have given you a problem to solve. I will provide the solution in the next session. Thanks for watching my lecture.